The United States aircraft carrier Saratoga presented damage control engineers with a fatal paradox. The massive carrier remained afloat after Baker, upright on the lagoon surface after a nearby underwater nuclear detonation. But the vessel was enveloped by a dangerous field of radioactive contamination. The Navy faced exactly two bad options. Commanders could order salvage crews onto the steel decks to rig emergency pumps and secure a tow line, accepting radiological exposure that commanders were not willing to impose during the short window in which the ship might still be saved. Or they could hold the safety perimeter, watching a highly engineered, fundamentally intact warship slowly flood until she slipped beneath the surface. The invisible boundary dictated the outcome. On July 25, 1946, the military initiated Test Baker inside the lagoon of Bikini Atoll. The overarching objective was to measure the physical survivability of naval architecture against atomic weaponry. A plutonium device boasting a yield of 23 kilotons was suspended deep beneath a landing ship in the center of the target array. The Saratoga, an immense fleet carrier weighing tens of thousands of tons, was planned for a 500-yard mooring from surface zero. But slack moorings and a wind shift may have carried her closer, perhaps within 300 yards, before the weapon fired. She was deliberately positioned to endure a catastrophic impact, but naval engineers did not prepare the ship simply to be thrown away. Saratoga's compartmentation was unusually complete, with more than 1,000 watertight compartments, and she went into the test in a near-combat-ready condition. Her lower hull and internal subdivisions were prepared to represent a hard, resilient warship rather than an empty hulk waiting to die. When the 23-kiloton device detonated underwater, the physical forces unleashed upon the lagoon were staggering. The immediate blast wave slammed into the target array, stripping away smaller vessels. Yet, as the turbulent water settled, the Saratoga remained stubbornly buoyant. She did not shatter into pieces, and she did not capsize. Naval observers circling the lagoon at a safe distance assessed the damage through their optics and determined that the core structural integrity of the ship survived the initial strike. Under a non-radioactive wartime scenario, this might have been the moment when damage control doctrine came alive. A heavy fleet tug could have tried to reach the bow. A crew might have attempted pumping, towing, or beaching before progressive flooding took control. Observers later believed she might have been saved had trained men already been aboard with pumps alive and boilers under control. But the Test Baker environment rendered conventional salvage doctrines useless. The underwater detonation had saturated the lagoon water and the surrounding target ships with lethal radioactive isotopes. A highly toxic base surge had washed directly over the exterior of the Saratoga. The flight deck, the island superstructure, and the surrounding surface water were actively radiating lethal energy, turning the carrier into a practical denial zone during the only hours that mattered. Some damaged vessels at the edges of the target array were later handled with extreme speed and tightly limited exposure. But Saratoga's survival window closed before a crew could safely be put aboard. Below the waterline, the fatal flooding could not be watched directly from the observing ships. Navy divers later inferred from oil leaks, hull tearing near the starboard quarter, and failed sea chests and valves that the bottom shell plating had been ruptured. Because the ship had been prepared with unusually strong watertight subdivision, the internal flooding appears to have advanced not as one instant collapse, but as a compartment-by-compartment loss of reserve buoyancy. The carrier's upright attitude made the process visible from outside, but it did not make the damage reachable. By mid-afternoon, a little more than 7 hours after the atomic detonation, the water was climbing over the after corner of the flight deck and up toward the island. The Saratoga slipped beneath the surface of the lagoon within hours of Baker. She simply traded the surface for the deep sea floor. The carrier descended largely intact and became a locked anomaly on the lagoon floor. In the early post-test period, radiation defined the boundary. In later decades, that boundary shifted to depth, remoteness, unexploded ordnance, heritage controls, and the demanding physics of deep technical diving. The placement of the atomic device locked the Saratoga into a fatal geometric trap. The Baker device sat 90 feet below the lagoon surface beneath LSM-60. That offset placed Saratoga in a narrow, destructive band. close enough to suffer massive hydrodynamic shock but far enough away to avoid instant vaporization. This spatial arrangement subjected the ship to two different physical forces from a single detonation. This specific spatial arrangement guaranteed that the ship would be subjected to two entirely different physical forces from a single detonation. The target was close enough to suffer massive hydrodynamic shock but far enough away to avoid instant vaporization. When the weapon fired, it did not hit the ship with heat or wind. It hit the ship with the ocean itself. The detonation instantly vaporized the water immediately surrounding the core, carving out an immense subterranean gas bubble. As this bubble violently expanded, it drove a high-pressure shockwave through the heavy liquid. Water is virtually incompressible, meaning the shock energy did not dissipate into the air. Instead, the pressure front struck the starboard side of the carrier like a solid wall of iron. It left a measurable signature in the shell plating and torpedo blister, where steel was dished inward by inches in some areas and by several feet in others. The unseen lower rupture, combined with progressive flooding, eventually pulled the vessel down, but the most devastating mechanism of destruction came from above. As the underwater gas bubble burst through the surface, it propelled millions of tons of lagoon water and shattered coral floor high into the sky. This formed a dense vertical water column thousands of feet tall. Physics dictates that this displaced mass cannot remain aloft. Gravity quickly overtook the upward momentum, and the entire mass of heavy water collapsed back toward the surface. The carrier sat directly beneath the expanding edge of this falling ocean. This produced the crushing signature seen across the upper ship. Blast-generated waves and the falling water column collapsed and compressed the aft flight deck. The funnel split, fell across the flight deck, and was left partly standing in 1946 before later collapse reduced it further. The upper mast and radar equipment were broken and scattered across the island structure, leaving the superstructure twisted, stripped, and visibly marked by the water column's force. As the massive column disintegrated and fell, radioactive water, mist, and fission products contaminated the target array far more severely than planners expected. Exposed surfaces, wood, paint, tar, rust, and grease could hold dangerous activity even after washing, making the falling column not just a mechanical force, but the main contamination mechanism of the test. Once internal buoyancy failed, the massive steel hull settled on the lagoon floor at a final depth of 180 feet. By the time Navy and National Park Service teams returned, the intense radiological hazard left behind by the atomic mist had decayed into the background environment. The problem had become access. 180 feet of water demanded strict deep diving procedures, redundant breathing systems, standard Navy air tables, and staged oxygen decompression, so every visit to the hull had to be short and tightly controlled. At that depth, pressure rapidly drives nitrogen into a diver's blood and tissues, creating the decompression limit that governed the work. Any productive time on the lower hull incurred a physiological debt, paid through long staged off-gassing stops in shallow water before the team could surface. The shallowest point of the wreck sat at 40 feet, while the structural evidence that mattered lay much deeper. In 1989 and 1990, the National Park Service Submerged Cultural Resources Unit partnered directly with United States Navy deep-sea divers to launch an extensive archaeological mission. The joint team's objective was to map the enormous site and establish a permanent, accurate structural record. To do that, they used detailed archaeological sketching techniques while hovering weightless in the dark water. They arrived on site with a disciplined archaeological doctrine. This was not a salvage operation, and it was not an artifact recovery mission. The investigators were there to document the nuclear test anomaly as it rested on the sand, using careful visual measurement, structural sketching, and photography rather than cutting into the ship or lifting objects from it. The governing rule was minimal disturbance, with safety exceptions handled by specialists when dangerous ordnance required attention. The massive structure could be surveyed meticulously, but it was not to be treated as a wreck to be stripped or recovered. This doctrinal boundary directly governed how teams interacted with the interior volume of the ship. Moving inside a dark, sunken structure drastically increases the risk profile of any deep dive, especially when the available bottom time is already tightly restricted by rapid nitrogen loading. The survey teams used accessible openings to enter selected upper spaces. They worked through the elevator area, the hangar deck, the island, the flag plot, the navigation bridge, the aerological office, the auxiliary radio room, and the windlass area. These spaces allowed the divers to sketch and map the atomic damage footprint along the documented upper route. However, strict operational firewalls still shaped the interior work. The investigators did not push into deeper, unlit engineering spaces or the lower compartments beyond the documented route. Boiler intakes were clogged with debris, open hatches led quickly into companionways and gun handling spaces, and further compartments aft were not entered. The combination of depth, silt, overhead entrapment, ordnance, and preservation discipline made those deeper spaces a poor target for an archaeological survey working on compressed air. Those protocols set the project's forensic ceiling. The team could document visible structure but could not convert the wreck into a laboratory sample. The destruction sequence had to be argued from exterior geometry and accessible intact steel. The deformed starboard steel provides the clearest geometric signature of atomic destruction, but the damage was not limited to 3 to 6 inches. 1946. Navy divers reported 3 to 6 inches of dishing in the central starboard hull, while the later survey found the torpedo blister pushed inward between frames to a depth of 6 feet in some areas. The plating was not simply shattered into fragments, it was bent, dished, torn, and distorted into a permanent physical record of the pressure front. By systematically tracing and measuring the starboard deformation, the archaeological teams achieved a critical positive knowledge gain. The pattern of dishing, tearing, and blister damage strongly supported the 1946 damage assessments and showed that the pressure wave struck the side facing the blast without immediately destroying the carrier's main longitudinal structure. Investigators could read much of the impact directly from the surviving hull architecture, while still recognizing that some cracks may have resulted from later settling rather than the bomb alone. The coherent condition of the massive hull provides further structural proof. The ship rests stubbornly upright upon its port bilge, locked permanently at a 10 to 15 degree list. This slight angular tilt is crucial for the investigators. It exposes the deformed starboard profile upward for clear visual mapping, while driving the opposite side heavily toward the lagoon bed. The overall continuous integrity of the upper hull geometry definitively proves that the sheer concussive impact failed to break the heavy keel or snap the long, longitudinal structure in half. The ship remains a single, continuous, highly coherent piece of naval engineering. However, the sheer immense scale of this intact structure establishes a definitive and unyielding proof ceiling. While the upper hull accurately records the incoming horizontal shockwave, the fatal wound that actually doomed the ship resides elsewhere. Early military damage control assessments concluded that the catastrophic, unmitigated flooding originated from a severe localized rupture torn directly into the deeply submerged bottom shell plating. To completely close the forensic loop on the actual sinking mechanics, the survey teams needed to visually locate and document this specific torn section on the absolute lowest extremity of the carrier. They quickly discovered that this final structural truth lay beyond the reach of a non-intrusive visual survey. The incredible dead weight of the intact, flooded warship had driven the lower hull deeply into the soft sediment of the lagoon floor. Dense silt packed around the bottom shell, plating up to the level of the propulsion shafts, physically blocking direct external observation. Because the main hull was pinned into the mud at a 10 to 15 degree list, the suspected lower rupture could not be verified without excavation, tunneling, or cutting that lay outside the project's mandate. The main hull provides perfect documentation of the incoming shockwave vector, but it irrevocably hides the final catastrophic failure that flooded the deep engineering spaces. With the lower rupture outside visual reach, the survey's next evidentiary move was outward, toward the boundaries of the impact zone and the fragments scattered away from the primary structure. The mandate to document the complete boundaries of the impact zone forced investigators to account for a separate local hazard. The ship still held ordnance placed aboard as test material, including racks of aerial bombs, depth bombs, rockets, and Mark 13 torpedoes in the hangar area. Some items were live or partially live, while others had inert elements or incomplete explosive trains. making the aviation spaces a safety problem as well as an archaeological target. Stepping carefully beyond the immediate internal threat, the investigators focused on what the wreck itself and the surrounding bottom could safely reveal. Baker's waves swept 5 aircraft from Saratoga's flight deck, and one starboard aircraft was recorded as blown over the side before the ship sank. Yet the survey did not turn those missing aircraft into a precise chain-snapping map. A brief search for one aircraft was unsuccessful, while the strongest documented aircraft evidence remained in and around the hangar: folded Helldivers, an Avenger, loose racks, detached engines, and test ordnance still lying where the ship carried them down. Moving further through the evidence, the surveyors also documented the violent damage to the island, mast, radar, and funnel. The top foremast was broken above the radar platform, antennae were sheared away, and pieces of the radar array lay tangled on the island structure. This damage served as upper-level evidence of the force that passed over the vessel, but it did not require inventing a separate off-hull mass field in the sediment. Inside the aviation spaces, that hazard became specific enough for Navy EOD personnel to confirm identifications and safe one fuse that presented an unreasonable risk. The documented threat was not a proven field of torpedoes and bombs blown free into the mud outside the carrier, but military ordnance remaining inside a deep, silty, deteriorating wreck. Light aviation structures submerged in salt water do not remain perfectly static. They exist within a slow, unforgiving shadow of risk. The flight deck, hangar supports, catwalks, and upper plating were already damaged by blast, waves, falling water, and later collapse. Decades of immersion added corrosion, biological attack on wood, silt loading, oil films, and gradual structural weakening. The danger is not simply the hydrostatic pressure of the lagoon crushing an already flooded ship, but the slow post-depositional decay of thin steel and damaged overhead spans. As the decades advance, that slow destruction presents a rising hazard to any human presence and gradually alters the original physical state of the site. Despite this creeping deterioration, the baseline survey achieved a crucial positive knowledge gain. By refusing to treat every unknown as a reason for permanent exclusion, investigators assessed the accessible structure, the hangar, the elevator openings, the island spaces, and the flight deck. Their work supported the possibility of controlled, highly regulated technical visitation under strict risk management. It did not prove the site safe in any absolute sense. Deep shipwreck diving at Bikini remained risky, and penetration at depth added another order of hazard. That access remained conditional rather than forensic completion. Relying on structural mapping, hazard assessment, and heritage management, the present condition of the sunken carrier is best defined as controlled and conditionally accessible. The site belongs to the protected Bikini Atoll nuclear test landscape, where remoteness, depth, technical diving requirements, ordnance risks, and preservation rules define access. Modern penetration diving has occurred, but only inside a regulated technical framework rather than a salvage framework. Today, the carrier functions as an observational baseline, not as a site proven to be monitored in every structural detail. Management guidance emphasizes inventory, safety controls, and periodic monitoring, while preservation rules limit human disturbance. The mighty vessel rests conditionally accessible, offering a profound, tightly controlled glimpse into a singular moment of extreme force, quietly yielding to saltwater, corrosion, silt, and time, while preserving much of its isolated historical geometry.